What? It's time for math class already? Let's do some math.
Calculus, early transcendentals. I can't wait to learn about calculus. You make me go mental. Logarithms aren't easy for me. When limits got you down and your mind won't work at all, don't worry about it, baby. Here comes L'Hopital. Calculus, early transcendentals, hyperbolic coaster catenary. Calculus, learn real world models when you make it to Calculus 3.
Hello again. In today's lesson, we are going to get a little bit more into this idea of limits. And to start with, we'll have a little bit more precise notion of what we mean by a limit, and then we'll spend some time on slightly informal techniques for calculating limits. And then in the next section that we cover, we're going to get into the really precise algebraic ways of computing limits. But today, we're just going to focus on getting the idea of limit and thinking about how to see what limits are both graphically and numerically. So let's start with our definition of limit. The first thing we have to do is suppose we got a function, and that function has to be defined for all the input values x near the point A, but maybe it won't be defined at A itself. Maybe it will, maybe it won't. In the definition of limit, we don't need the function to be defined at the point A. The idea is that if we can make the function f of x as close to some number L as we want, just by choosing our values of x sufficiently close to that value A, then when that happens, we say that the limit as x approaches A of f of x is equal to L. So you see the notation in yellow there. You got the lim with the x with an arrow pointing at A. So that reads the limit as x approaches A, and then of f of x equals L. Let me try to draw a picture of what this somewhat formal definition is getting at. So let me draw a coordinate system here, and I've got some function. Doesn't really matter what, just there's some function f. And then we got some point A on the x-axis that we're interested in. What's going on with that function there? Now, if this function has a limit equal to L, then you can kind of see that graphically. That'll be what the y value is on the graph there, if there is a y value at that point. And the idea is in that definition that we can make f of x as close to L as we want. If we take some target area around L there in red, so there we're saying we want to be that close to L, then we can find the x values that will fall into that target. So as you can see from this picture here, as long as I choose my x pretty close to A, within this region right here, highlighted in blue, as long as I choose my x there, then I can see that when I plug that into the function, the output value is going to be within that desired tolerance that I placed around L at the start. So there's my f of x. So this picture is capturing the idea that the limit as x approaches A of the function f of x is equal to L. But graphically, you can kind of just see it. The limit is essentially what the y value is on the graph if there's a unique y value going on. Sometimes there's not. So let's look at this example down here. One thing that's very important in this definition, which I will highlight here, we can make f of x as close to L as we want by choosing x sufficiently close but not equal to A. So when we're thinking about limits, we really have to avoid thinking about exactly what happens at A and only think what happens when the x is close to A. So if I go back down to this example at the bottom here, let's think about when I plug in an x, let's focus on 3 for a moment. If I plug in an x value that's really close to 3, what do those y values look like they're coming out close to? Now I want to avoid plugging in exactly 3 because in the definition of limit it tells us explicitly don't do that. Don't plug in exactly 3. So here, what does it look like the limit as x approaches 3 of f of x is? Well, it looks like to me that when I plug in x's that are closer and closer to 3, that the y values are getting closer and closer to 2. Now, you can see in that graph, there's a little hole in the graph there. And that actually, the value of the function at that point, f of 3, is equal to 4 in this case, right? So the moral of the story here is that the limit of the function isn't necessarily just what the y value is of the function at that point. It's what the y values on the graph of the function are getting close to around that point, but not at that point exactly. So here we see the limit's equal to 2 at 3, but the function value at 3 is equal to 4, which is a different number, right? So the moral of the story is these two numbers here, maybe they're not equal. Most of the time they are equal, but it's not necessarily true. And then if we look at this other point on the graph here, I'm interested in what is the limit as x approaches 5 of f of x. It's the same sort of consideration. I think about what happens when I plug in an x value that's really close to 5. What happens to the y values? And from just playing around on the graph here, just sort of visualizing what happens when I put in x's that are close to 5, it looks like to me that the y values, the function values, are getting close to 3. Even though the function itself, you see on the graph there's a little hole there, that means the function's not even defined at that point. It's not necessary that the function be defined at a point for the limit to exist at that point. Because again, in the definition, we only wonder what happens when x is sufficiently close to a, but not equal to a. Graphically, you should be thinking, what are the y values getting close to at the point? Let's think about this from a more numerical standpoint. So here's an example. I've got the function f of x equals 9, or x minus 9 over the square root of x minus 3. And I want to know what happens when x is near 9. And from considering a table of values where I plug in values of x that are close to 9, I want to make a conjecture for what this limit is right here. What is the limit as x approaches 9 of f of x? You know, we could manually go and make a table where you remember doing this in the previous section where we just made a little table and we put in values of x. Like if we're thinking about values of x close to 9, I might put in like 9.1, 9.01, 9.0001, and so on. And I might put values that are a little less than 9 too. Like I could put 8.9, 8.99, and so on. I'm going to show you a pretty cool app that you can access online, and maybe you already know about this. So if you Google Desmos, it gives you a really cool graphing calculator, but it also is a really cool way to make tables of values. So I'm going to put in that function, which was x minus 9, and then we divided by square root of x minus 3. And I was curious at what's going on with that function around x equals 9. When you look at the graph, there's nothing remarkable going on at the x value of 9. It just looks like the y value is about 6. So already I'm thinking probably the limit is 6. But let's look at it from a numerical standpoint. What you can do here is go to this table form of it, and I want to look at values around 9, so I'm going to modify that table on the left to be values that are getting close to 9 but not equal to 9. So let's do, how about start, I'll do numbers that are bigger than 9 and then getting closer to 9. So like start with 10, and then I could do 9.1, 9.01, 9.001. Of course, if I try to put in exactly 9, you see what happens. Oh, it should be 9.01 there, put a comma. Anyway, you see what happens when you put exactly 9. It's undefined. And then let's put some numbers that are a little bit less than 9, like 8.999, 8.99, 8.9, maybe just 8. Great. Let me steal this little table of values and bring it back to our notes that we're making there. Okay, so there's the table of values that I wanted to make a conjecture about the limit as x approaches 9 of f of x. And so what I want you to be noticing from this table is that when these values of x here are getting closer and closer to 9, but not equal to 9, because we can't plug in 9 exactly, that's undefined. But as those values of x are getting closer and closer to 9, either way, whether you look at it as the values of x are getting close to 9 but bigger than 9, or if you look at those values of x are getting close to 9 but those values are less than 9, either way, as those values close in on 9, what are the y values doing in the right-hand column? It looks like to me that these values are closing in on 6. So my conjecture, based on the table, is that the limit as x approaches 9 of x minus 9 over square root of x minus 3 is equal to 6. Now, is that a proof? Maybe there's something weird going on. If we had plugged different numbers into that table, we would have started getting different results. But boy, when you combine that with the graphical evidence that the grapher provided, looking at this graph here, when I focus in on the x value of 9, which is right about there, well, I didn't get the y-axis, but we could see by looking at it a minute ago that on the y-axis it was coming out to about 6 there. So either way, looks like 6. Feel pretty good about that one. So the next thing we want to talk about as we start talking about limits is the idea of one-sided limits. We're going to have the idea of a right-sided limit, or maybe I'll say right-hand limit. And then we'll also have the idea of left-hand limits or left-sided limits. The sort of formal definition is basically the same idea as before when we were just talking about regular limits. So regular limits, like we talked about before, we may refer to that as a two-sided limit. The definition of one-sided limits is basically the same as the definition was for two-sided limits, but the main difference is when you're thinking about a right-sided limit, when you think about your function, you only worry about the values of x that are bigger or larger, greater than the value a that you're focusing on. So a is the place where you're taking the limit. So I'm only going to worry about the function being defined for x bigger than a. Same idea, if you can make your function values as close to this limit L as you like by choosing your x's sufficiently close to a, but with x bigger than a. And notice that saying x is strictly greater than a excludes the possibility that x is equal to a. So we still have the same thing as before where we're not allowing x to be equal to a. But if you can make those function values as close to L as you like, then as close as you like to L by choosing your x's close to a but greater than a, then you use this notation to express that scenario. So this reads the limit of f of x as x approaches a from the right. So you see the main difference in the notation is the inclusion of this little plus sign right here. And then we have a similar, the similar definition for the left-sided limit. So now you're thinking about values of x that are less than a, or if you think about it on a number line to the left of a. We'll have a very similar notation for when the limit from the left equals L. Instead of a little plus sign above the a, we have a minus sign to indicate the left side here. And then we say the limit of f of x as x approaches a from the left is L, whenever that happens. The main thing is it's the same idea as before, but you're only thinking about the values of x on one side or the other of the value a that you're interested in. So if you're looking at values on the right, that's a right-sided limit. And if you're looking at values on the left or less than, then you're looking at a left-handed limit. So think about this example right here. I'm interested in what's happening at 4. So 4 is going to be my a. So what's the limit as x approaches 4 from the right-hand side? So I'll put the little plus there of f of x. What would that be equal? And also I want to know what is the limit as x approaches 4 from the left. Well, looking at the graph, if I would take values of x that are a little bit bigger than 4 and put them into the function, what do the y values get close to? Well, it looks like those y values are going to be getting really close to 5. based on this graph, I would say the limit as x approaches 4 from the right-hand side is 5. On the other hand, when I look at the values of x on the left-hand side of 4, or less than 4, so plug in some of those x's into this function and see what the y values are getting close to. And it looks like to me that those y values are getting very close to 2. Now notice, I never plug in 4 exactly. So if I would plug in 4 exactly in this function, I would get 5, which happens to be the right-hand limit, but it's not the left-hand limit, right? Again, the idea is think about what the values are. You think about values that are close to the point in question, 4 in this case, but not equal to it. Very important to think that way. Okay, so there's the graphical idea of one-sided limit. Let's look at a more numerical form of it. So here I've got a function, f of x equals x minus 9 over square root of x minus 3. And I'd like to make a table of values for that function whenever x is getting close to 9. And then I want to make a conjecture about what the values of these two one-sided limits are. The right-sided limit and the left-sided limit here at x equals 9. Well, hold on a second. This is the same function we looked at just a minute ago. And we already made that table. Let me just go over there and grab it. Okay, so let's think about the right-hand limit first. The limit as x approaches 9 from the right-hand side. And this time the function that we're examining is x minus 9 over square root of x minus 3. Okay, well, the values of x that are larger than 9 but getting close to 9 in this table are these ones, right? So here in yellow, go from 10 to 9.1 to 9.01 to 9.001. I can see that those values of x are close to 9 but not equal to 9, or getting closer. And I can see the progression of the y values in the right-hand side of the table. And those values right there appear to be getting close to 6. So over here in yellow, you see you've got the x's are going to 9 from the right, because those values are larger than 9. So looks like to me the right-hand limit, the right-sided limit, is equal to about 6, looks like to me. And then if we look at the values of x approaching 9 from the left-hand side, so we look at the left-sided limit, well, they're also getting close to 9, right? As I see the values progress from 8 to 8.9 to all the way up to 8.99, and homing in on 9, but coming in from the other side. So here we have our x's are approaching 9, but from the left-hand side, looks like those values are also getting close to 6. So that answers that question. There's something interesting going on here, though, which is the reason I chose this example. So we see that the left-hand limit and the right-hand limit, they were both equal to 6 here. So I just want you to remember, when we looked at this example earlier, we also said that the two-sided limit, we also said that was 6. So this is kind of what you would expect. If the two-sided limit's going to equal 6, you would expect the individual one-sided limits, the right-hand limit and the left-hand limit, should also both equal 6. I mean, how would it be possible that the right-hand limit would be 6 and the left-hand limit be 7, but somehow the two-sided limit be equal to 6? So the idea is that when the two-sided limit equals a number, the left and the right-hand limits had better agree with that. So actually, this is a pretty important theorem. So when you see the word theorem in math class, it means it's an important fact. And it also means that it's something that has been proven to be true. So it's not something that we're guessing about. It's that mathematicians have a very rigorous mathematical proof that it's true. So this theorem 2.1 captures the relationship between one-sided and two-sided limits. So the setup for it is our function f has to be defined for all the x's near a, except possibly at a. Remember, when we're talking about limits, we don't care what happens at a. Just we need to know what's happening around a. So this thing says that the two-sided limit as x approaches a is equal to L if and only if both of the one-sided limits at that same point are equal to L also. So this is a pretty useful theorem, and let me give you a few ways that you can interpret what it's saying. What we can conclude on the basis of this is that if you know that both of those one-sided limits are equal to L, then, so if you examined somehow the one-sided limits separately and got the same answer, they agreed, then it tells you automatically that the two-sided limit is equal to L also. But another thing you can observe is that if one of those two-sided limits does not exist, so if you find out that the limit as x approaches a from the right just does not exist, or if the left-hand limit would not exist, you only need one of them to not exist, so that's why it's an or. So D and E does not exist, of course. If either one of those one-sided limits does not exist, then the two-sided limit does not exist. So this can happen whenever the function has an asymptote or something like that, and maybe it's going to infinity. We'll be talking about infinite limits pretty soon, so we'll make that a bit more precise. Also, a third thing I can point out is that if the limit as x approaches a on the right, let's say, just does not, maybe it exists, but it just does not equal the limit that you get on the left-hand side. So if the left-hand limit and the right-hand limit do not agree, then we can also say that the two-sided limit does not exist. That's a pretty powerful tool. It gives us a way, especially 2 and 3, I think, are especially nice. But all three of these observations are really nice. Let's apply it to a few different examples. So here's an example. The function is x cubed minus 1 over x minus 1. So those of you that are feeling really good about your algebra might recognize that, wow, that looks like something that might factor and simplify. And that's true, but I'm not going to worry about that right now. So I've got this function, and I want to use one-sided limits to either find the value of the two-sided limit at x equals 1 or show that it doesn't exist. Let's go to that Desmos utility and have a look at the graph and the numerical values of what's going on there when x is getting close to 1. Now, please recognize that you can't plug in x equals 1 here. If you try to plug in x equals 1, you divide by 0, which causes the universe to explode. So you don't want to try it. So we want to be careful to stay. We put things very close to 1, though. Interesting, it's a parabola. And I'm interested in what's happening around x equals 1. So let me kind of zoom in on that portion of the graph. And let's put it into the mode where we can put in a table of values. So since I'm interested in what's happening at 1, let me do values from the right, so sort of in decreasing order. So I'll put in 2, and then say 1.1, 1.01, 1.001, something like that. If I try to put in 1, of course, the computer says undefined. We were expecting that. And let's put in values that are getting close to 1 from the left-hand side. So maybe put in 0.9999, 0.99, 0.9, 0. I think that's probably enough values to get the sense of it. So we wanted to use one-side limits to either find the limit as x approaches 1 or show that it does not exist. Well, what I'm seeing, both from the numerical and from the graphical, is that as the values of x approach 1 without being equal to 1, so here I got x is going to 1 from the right, here I've got x is going to 1 from the left. It looks like to me either way, they're getting close to about 3. And also on the graph here, and when I put in the value of 1 into this function, it looks like it's getting close to 3 there too, right? On both sides. So if I plug in some x's on the left-hand side, those x's are getting close to 3. And if I plug in values of x that are on the right-hand side, we can see graphically those y values are getting close to 3 also. So graphically, numerically, it looks like the situation is this. Limit as x approaches 1 from the right equals 3, and limit as x approaches 1 from the left is 3. So that previous theorem tells me that since those two one-sided limits exist, this was theorem 2.1, by theorem 2.1 we can conclude that the limit as x approaches 1, the two-sided limit, is equal to 3 also. So even though algebraically that function had a serious problem with x equals 1, it was well behaved on both sides of 1, where the y values were converging on 3 from either side. So that, and when you see the graph of the function, it doesn't look like anything horrible is going on there. What's really going on with this function is that it's just missing one point. Like right here at x equals 3, there's a little hole in the graph, but it's a microscopic hole consisting of only 1 point. So the grapher, there's no way for it to depict that hole. So it just looks like it's going continuously through that point. But in fact, there's a tiny hole there in the graph that you can't see. Let's do a couple more examples with this one-sided limit idea. Oh, here's a weird one. I want to use one-sided limits to evaluate this limit as x approaches 3 of this function, which is x minus 3 divided by the absolute value of x minus 3. Let's use the technology to help us out again here too. Very soon we'll be able to handle this algebraically, but for now we'll use the computer to help us out. So let's go over here to Desmos and let's put in that function, and let's see the table of values. And I'm focusing on what happens around x equals 3 because that's the weird place, right, where it's like getting a 0 in the denominator. So I'll put in, say 4, 3.1, 3.01, 3.001, and then I'll put some values that are, if I try 3, of course, it says undefined. Then I'll do some numbers that are a bit less than 3. Notice that as I was punching in those values, it puts little blue dots on the graph corresponding to those points. Of course, the ones that are really close together, they get kind of bunched up near 3. But in any event, let me do a grab of this. So my job was to use one-sided limits to evaluate that two-sided limit. So here's what I'm seeing, both numerically and from the graph. It looks like the limit as x approaches 3 from the right-hand side looks like it's always equal to 1. So the limit would be 1. Graphically, if I put in these values that are close to 3 but a little bigger than 3, the y values always come out to 1. And then likewise, if I put in values of x that are less than 3, the y values come out exactly equal to -1. So the left-hand limit is going to be -1. These two things are unequal. So that previous theorem that we were talking about, 2.1, that gave the relationship between one-sided limits and two-sided limits, tells me that the two-sided limit does not exist. So this function's limit at 3 does not exist. Even though its one-sided limits do exist, but they're not equal. So if the one-sided limits, even if they exist, if they're not equal, then the two-sided limit does not exist. Okay, one more example. Similar sort of thing. Got a function I want to take the limit of. The function is x minus 1 over square root of the quantity x minus 1. And I want to see what's going on near x equals 1. X equals 1 is very mysterious because, it causes division by 0, so maybe something interesting is going on there. Lots of times when you end up dividing by 0, it blows up and it sort of goes to infinity. But sometimes not. So, well, let's go to Desmos and see what's going on with this function. So there's a graph of that function, and let's look at the table of values. Interesting. You see in that table there, all those values of x that were less than 1, it's telling me undefined. Why is it undefined? Well, if you think about it, if you put in something less than 1, the number that's inside the radical is going to be negative. Like when you put in 0, you get 0 minus 1 in the radical down there, which is -1, and so you try to take the square root of a negative number. And while you may have heard of complex numbers, we're not dealing with complex numbers in this case. So whenever a negative appears in a radical, it's a problem for us. So we'll consider those sort of situations just to be undefined. From this table, from this graph, we can see that the limit as x approaches 1 from the right-hand side, the limit as x approaches 1 from the right, it's not a problem. It looks pretty clear from the table that as you put in values of x getting closer and closer to 1, that the y values are getting closer to 0. On the other hand, we got a problem when we try to let x go to 1 from the left. The limit as x approaches 1 from the left simply does not exist, and the reason it doesn't exist is because f is not defined when x is less than 1. So if the function's not defined, the definition of limit doesn't make sense, so you just say you don't have a limit. Limit does not exist. And so because of that theorem 2.1 that we talked about earlier, it says that if one of the left-hand limit, if one of the one-sided limits does not exist, then the two-sided limit doesn't exist. So we can say by the theorem 2.1 here that the limit as x approaches 1, the two-sided limit, just does not exist. We need both the left-hand limit and the right-hand limit to exist and be equal is the point. So that limit does not exist. In our next lesson, we're going to get into the algebra of these things. How do we analyze these things without having to go to Desmos and punching it in and getting kind of a guess? You might wonder, well, gosh, it seems like the computer works great. Why don't we just do that all the time? But in fact, I can come up with several examples where you put in the function and Desmos just has no idea what to do. Or maybe I can come up with examples where you put in a reasonable number of test values to form a table and it gives you a misleading answer. A classic example of this is the function sine of 1 over x. And you look at what's going on near x equals 0. What is this graph telling you about the behavior of the function whenever x is equal to 0? I'm zooming in here at x equals 0. Can you tell what's going on? I'm zooming in, man. I'm getting really close. I still can't tell anything that's going on. It just looks like a haze. Something weird is going on there at x equals 0, right? This graph can't give me the answer. And also, the table of values wouldn't help me out either, because which values do I pick? It's going to give me a bunch of weird stuff. Anyway, so you have to exercise some caution when you're dealing with these graphs. They can be misleading. And that's why we want algebraic techniques, because they tend to be a bit more reliable. Okay, I'll stop there. See you next time.